Right, here we have the experiment where we're going to investigate the principle of conservation of momentum, which, as we know, says that the total momentum of a system is the same before and after a collision, provided no external forces act. Right, now the two things we're going to be colliding today are these two fellas, two PASCO Smart Carts. We've seen something similar before. We've seen me use carts and light gates in the F equals MA practical, but these are slightly different. These are actually smart carts. Okay, instead of using light gates or having to use light gates, these fellas include an internal motion sensor which can actually simultaneously measure displacement, velocity and acceleration at the same time. But we just want velocity because we want to see what's momentum before and after. So as long as we know the mass of these and we know the exact velocity, then we can work out momentum before and after the collision. Right, what's the mass of these two fellas? Well, each one of these measures 270 grams or 0.270 kilograms. And we're going to vary the mass by adding these fellas, which these metal blocks, iron blocks made of 250 grams each. So we're going to add those to either one, and then we can move the trolleys in and have some collisions and measure the velocities before and after. Okay, right, two sets of collisions we're going to look at. The way we're going to analyse is we're going to use Sparkvue again, like we did in the last practical, but instead of displaying the values of velocity as a value, it's actually going to record and plot in real time graphs of velocity against time, because as we know, the velocity is going to change before and after the collisions. Okay, I'll just quickly show you that. So if I start recording, okay, right, so we've got a red and a blue, so backwards, negative velocity, forwards, positive velocity, backwards, forwards. Same with the blue, backwards, negative, forwards, negative, backwards, negative, forwards, negative. Okay, so that's pretty much it. And we can read the exact value of the velocity at any point. I'll show you that in a minute. Right, so let's get rid of that. Manage runs, delete last run. Thank you very much. Now we're ready to go. Just one last thing. Your document. Right, this is for you to record your data. Right, I've shared this with you, but if you have a look down, there's two tables. We're going to do 5 elastic collisions and 5 inelastic collisions. Okay, so how are we going to have elastic and inelastic with these two trolleys? Right, elastic, as you should know, elastic collisions is when kinetic energy is conserved in a collision. Okay, now the way we can get that, or where we can get close to that, is right, the two trolleys have two opposing magnets on each end. So when it comes in, it's going to repel it. Now you can actually get a collision where there's actually no physical contact between the trolleys, as long as they're not going too fast. Okay, so that's how we're going to get elastic collisions. Now inelastic, we're going to use the other ends, okay, because they have Velcro. They have Velcro. Now the inelastic collisions, I'm going to get the trolleys to stick together on impact. Okay. Right, I think we're in business. Right, so we're going to start with the elastics. So as you can see, the two opposing magnets produce a collision like that. Okay, or like that. Right, what's first up in the table? Okay, first up. Right, 270 and 270. So this is the first elastic collision. Right, I'll start with the blue being stationary, and the red is going to come in at a certain speed. Okay, right. So 270 and 270. So 0.270, 0.270. That is just the trolleys on their own. Okay. So like I said, blue, the initial velocity is going to be 0. Right, what's the red going to come in at? What's the red going to finish at, and what's the blue going to finish at? That's what we're going to find out now. So I'll run you through filling in the first one. Start. Okay, so to analyse, right, let's rescale. Now, as we can see, the red comes in at a certain speed, certain velocity here. The blue goes off at a certain velocity here. The initial velocity of the blue is 0. The final velocity of the red is 0. Now, how to analyse, how to get these values exactly? We use this crosshair tool here, which is pretty neat. So there you have it. Initial velocity of the red, 0.443 meters per second. Initial velocity of the blue. Okay, initial velocity of the blue, as we can see, was 0. So the initial velocity of the red was 0.433. 0.443 meters per second. Right, what about the blue? The blue started at 0. The red ended at 0, but the blue went off at... The blue went off at... Okay. 0.438. 0.438 meters per second. Right, so there you have it. There's your first row in the table. Okay, right. You're going to populate the table on your own now. Okay. But the next up, what do we want? Right, next up in the table, we want 270 and 520. Again, I'll start with the blue stationary, but we want one of those. So 250 grams plus 270 is 520. So there's the blue. Red's going to come in. Okay. Okay, interesting. Right, we've got the red actually recoiled there, didn't it? So let's analyse this. So let's start with the red. The red. So we want just before the collision, don't we? Just before the collision. So the red came in at 0.650. The red recoiled at minus 0.181. Okay? Blue. Blue started at 0, didn't it? But the blue went off at 0.428 meters per second. 0.428 meters per second. Right. So there's run number 2. The second row in your table. What's next? Second row in the table. Third row in the table. We want 520 on red. So that's one of these on the red. And the blue's on its own. 270. Okay. Again, let's start with the blue stationary, and then we'll do a couple of head-on collisions. Right. Are we ready? The red did not recoil there. It didn't rebound. It carried on going, didn't it? In the same direction. Right, let's analyse. Red. Initial velocity of the red. Like that just before the collision. 0.512. Final velocity of the red. 0.162. Okay. Blue. Initial velocity was 0. Yeah, this is not to scale, by the way. As you can see, the scales are slightly different for the red and the blue. Final velocity of the blue, we're going to go with 0.658 meters per second. Okay, what's that one? That was number 3. That's run number 3. Right, run number 2. So it's run number 4. Because 4 comes after 3. Run number 4 is... Let's have a look. 270 and 270 again. Right, we're going to have a head-on collision now. We're going to have a head-on collision. So, let's start the recording. So this is run number 4, isn't it? Resize. Okay. Right, we have initial, so let's red. Initial velocity of the red. 0.573. Final velocity of the red. Minus 0.301. Blue. Initial velocity of the blue. Minus 0.365. Final velocity of the blue. .500. Okay, that is number 4. Number 5, as we can see in the table here, what we want 770. So we want an extra 250, 500. So that's now making, the red is now 770 grams. Blue's on its own. Okay, so this is the final one. We'll go for another head-on collision here. So let's go. Right, quite a big recoil there, isn't there? On the blue. So stop, rescale. Okay. Red. That's blue, isn't it? Initial velocity of the red. Somewhere up there. I'll do 0.489. Final velocity of the red. 0.103. Blue. Right, just before the collision here we want, just before the collision, I think that is the data point we want there. Minus 0.266. Now after the collision is .756 meters per second. Okay. So again, not to scale, that's important. That's the elastic collisions. Right, inelastic. What have we got? Inelastic. Okay, down to the inelastics. So we're going to start with 270 and 270 again. Now, we need Velcro to Velcro. Okay, now these guys are going to stick together on impact, which is nice. One thing I just need to do, I just need to change the sign, because the cars are now going backwards. That'll give us negative velocities. So I've just changed the signs there, so that should give us positive velocities, because I want all the velocities in this direction to be positive. All the velocities in the direction that the red initially moves as positive. Okay, right, let's go. So 270, 270. That is that one. We are going to have blue stationary, aren't we? Let's start with blue stationary again. Right. Now the red and the blue, they stuck together. They moved off at the same speed. So as you can see here, this speed and this speed are the same, but they're just not drawn to scale. Anyway, initial velocity of the red is up here. That'll do. 0.466. Final velocity of the red. 0.234. Initial velocity of the blue, 0. Final velocity of the blue, okay. Yeah, close enough, isn't it? 0.232. Okay. There you go. Right, so yeah, final velocity of the red, 0.232. Final velocity of the blue, 0.232. Okay, that should make sense. We want the two velocities to be the same because they stuck together and moved off, didn't they? Right, they moved off at the same velocity. Next up, so run number 7, which is the second inelastic. Yeah, the second inelastic. Right, we want 270 and 520. So 520 on blue means we need to put 250 in. Okay? Right, again, let's have the blue stationary. Let's start with the blue stationary. Right. So again, moving off at the same speed, rescale. Right. Red. Initial velocity red. Initial velocity red, 0.481. Final velocity red, 0.165. Initial velocity blue, 0. Final velocity blue was just after the collision. Okay. Okay, we've got a slight discrepancy. Well, we'll go with that one there. Okay, so they're both the same. Right, so final velocity of the red, 0.164. Final velocity of the blue, 0.164. Okay. Right, you can actually move along data points quite a lot like that. So, yeah. Okay. That was number 2, the second inelastic, wasn't it? Right, it's the third inelastic. What do we got? 770 on red, 270 on blue. So what do we got to do? 770, we need 2 of them. So 770 grams, so that's 500 plus 270. And then blue is 270. Right. We'll do blue stationary again, just because I want to show you if you've got a really big incoming mass, what's going to happen there when they stick together. Right, where are we? Let's go. Sparkvue. Let's start. Right. Rescale. Okay. Red. Initial velocity red. 0.406 meters per second. Final velocity red. 0.301. Okay. Initial velocity blue 0. Final velocity blue. That'll do. 0.301 meters per second. Okay. Next up, we'll finish off with 2 head-on collisions now. Right, we've got 520 on blue, so we need one of those on blue, and we've got 1020 on red. So that's the 3 250s. And the 270 makes 1020 grams. Right, we're doing a head-on collision now. How exciting. Ready? Nice. Right. Rescale. Okay. Red. Initial velocity red. 0.474. Final velocity red. 0.234 meters per second. Blue. initial velocity blue, so yeah, just before the collision, if you don't mind, minus 0.249 meters a second. Final velocity of the blue, it should be the same as the red, shouldn't it? Because they moved off together. They did move off together. That'll do. Not zero, because it's in the direction of the red. 0.234 meters a second. Same as the red, because they stuck together and moved off together. Last one. How exciting. What do we want for the last one? So 270 on red, but 1,270. So that's all on blue, isn't it? All four on blue. So an extra kilogram on the blue should do it. Okay. We are in business. Well, we'll have one more head-on collision now. So, back to Sparkvue. Last one, boys and girls. Head-on collision. Right. So yeah, the collision's here, isn't it? The collision is happening here. Let's resize. Okay. So let's analyze the red. Initial velocity of the red is up here. Initial velocity of the red, 0.606 meters per second. Final velocity of the red was backwards, wasn't it? Final velocity minus 0.056. Initial velocity of the blue. Okay. Just before the collision there. Right. You might see there's quite a noticeable decrease in the velocity of the blue before the collision. Because of, any ideas? It's friction. Okay, there's quite a lot of mass on there, so there's a lot of friction. So anyway, minus 0.209 meters per second. That's the initial velocity of the blue. The final velocity of the blue, which is the final data point from this practical, drum roll please, is minus 0.057 meters per second. That should be the same as this, shouldn't it? Okay, close enough. Close enough. Okay. There you have it, boys and girls. Elastic and inelastic collisions. Right, just last thing for you is we've got a table. As you can see in the table, we've got total momentum. Well, that's the total vector sum of the momentum. All right. So remember, going in the direction of the red is positive. Going in the opposite direction is negative. So you have to take that into consideration when calculating the total momentum, the total vector sum of the momentum of the two carts. Now you need to do that before and after the collision, and then see if momentum is conserved in each case. Second part though, I want you to work out the total kinetic energy of the two carts before and after the collision. So that's the total KE together. So you need to work out individually the kinetic energy of the red before, the kinetic energy of the blue before, and then use K equals a half mv squared, add those two values together, that gives you the total kinetic energy. And I want you to do that for before and after the collision. And I want you to see if and when kinetic energy is conserved. Okay? Right, there you have it. We have conservation of momentum and maybe kinetic energy using the PASCO Smart Carts. Thank you.